I have a gift for you. These are now uploaded on Canvas. This is uploaded directly underneath the chairs and absolute configurations worksheet on module Unit 2 module. So if you are someone that likes to have this downloaded instead, or if you want to come back to it and get a fresh copy, you can get it from there. We're going to spend some time utilizing this today. Here's how I want to start, is actually looking at the top 3 structures. Good point. I didn't number the sides. So this side, lawsone and oxycodone on the top. I want you to look through those molecules and identify as many chiral carbons as you can. Do you remember the requirement for a carbon being chiral? Must be connected to 4 different things. So look through it and see how many chiral carbons you see in oxycodone and lawsone. You can work together. Sarah, we're working on these 3 molecules, identifying as many chiral carbons as we can. Yeah, a lot of the double bonds remove any chance. And Sarah, if you want to work with Peter, feel free to shower. There's a double bond. It has 4 bonds, sure. Yeah. But it's connected to 3. Yeah. Are you including hydrogen? There's no hydrogen on that carbon. See it? I did see this. So there's only 1 carbon that's even an option. I think I might have found it. This is the only one bonded. Gang, are they 4 different? This intersection right here. This is CH2. This is C. At this carbon. Oh, this is the only one that's bonded for things. Is it bonded to 4 different things? 2 of them. No, yeah, that's right. Good. And then this is an oxygen and here's an applied hydrogen. So each of these groups, so this is bound to a CH2. the bottom right.
This is bonded to four things, but not four different. Yeah, that's true. So you're missing one carbon on the oxycarbon. Are you circling the ones that you can get?
Yeah, I'm just kind of going through them. This one, I think this one, there's a different. This is CH2. This is C. This is CH. This is N.
All right. How many chiral carbons in lawsone? 0. How many carbons in lawsone could even possibly be chiral? How many can we even begin to investigate? 2. Which 2? Here, it is bonded to it's bonded to 4 things, but 2 of those things are hydrogens. So it cannot be chiral because it has 2 identical groups. Well, it's also bonded to 2 carbons. Aren't those 2 identical groups? No. Those 2 carbons are not part of identical groups. This carbon is a part of an aromatic ring. This carbon is a part of an alkene within the same ring. Those are not the same, correct? Same element? Yes. But we don't say that a chiral carbon is bonded to 4 different elements. Chiral carbons are bonded to 4 different groups, no matter how far you have to go to get there. What was the other carbon that you thought we could investigate? Was it this one? Yeah. All of the other carbons in here are sp2 hybridized. So by the way, if you have 4 different groups, you must be an sp3 hybridized carbon. If you are not an sp3 hybridized carbon, like this carbon, you're not bonded to 4 different groups. Here's 1, 2, and 3. sp2 carbons, never chiral. sp carbons, never chiral. And I just lied, because there's like one exception of a molecule that is an sp carbon chiral center. So 99.999% of the time, and all of the molecules you're going to see from my class, they're sp3. Okay? I want you guys to similarly take just 5 minutes, go through bisphenol A glycidyl dimethyl tretinoin, ibuprofen, and those, hold off on those sugars. Just go through those middle 3 and circle as many chiral carbons as you can find. By the way, for those of you that missed it, I stole these from you. You should recognize at least one of these. Actually, that's not true. I didn't steal everybody's. But all the molecules on this sheet I got from your analysis assignments. Makes it easy for me. Thank you.
Just circle the carbon more than 100%.
Should I walk you through oxycodone now? Should we go through oxycodone? Because I meant to.
Well, yeah, but it has to be 4 separate.
Yeah, because it's going to make it easier for you to do the other 3 once we look at a compound that does have chiral carbons. How many chiral carbons did you find in oxycodone? 4? So first of all, we can rule out all of these sp2 positions, correct? They're never going to be chiral. And we can rule out CH2 positions. Those are never going to be chiral. Well, believe it or not, that eliminated all of our carbons. Oh, here's another CH2. That eliminated all of our carbons except for this one, this one, this one, and this one. CH2 groups, never chiral. sp2 carbons, never chiral. So let's prove what's going on here. This carbon is bonded to a tertiary alcohol carbon. I'm going to clear out some of this just to make it a bit easier to look at. Oh, there was another carbon I didn't cancel. The CH3, never chiral. This carbon here is bonded to a tertiary alcohol carbon. It's bonded to a nitrogen. It's bonded to a CH2, and it's bonded to a hydrogen. Those are 4 distinct groups, and I didn't have to go very far. This carbon here is bonded to an oxygen, a secondary amine carbon, a CH2, and a quaternary carbon. Those are all different groups. This carbon here is a quaternary carbon. That means it's bonded to carbon in each of its 4 bonds. We need to prove that all 4 of those carbons are part of different groups. Well, here's a CH2 that goes into this amine bridge. Here's a tertiary carbon that's adjacent to the ketone and the ether. Here's an sp2 carbon in the ring. And here is that tertiary alcohol again. So 2 tertiary carbons bonded to different groups in very different places. That's definitely a chiral carbon. And then lastly, I've got my hydrogen, my oxygen, my ketone carbon, and my quaternary carbon, all 4 different groups. If you can put to words a distinction between the carbons that it's bonded to, then those are different groups. Ketone carbon versus quaternary carbon, those carbons are not the same group. Does that make sense? 4 chiral centers in oxycodone. I'm not your biology teacher, so I do not feel at liberty to say that these are the absolute configurations they must have to be processed in your body, but I would bet it is. So not only does it have 4 chiral carbons, but those 4 chiral carbons most likely need to be arranged in that way. You can't change any of their configurations from R to S at all. All right, head back in. Yeah.
Question. In my mind, that top one, I see how it is, but I was thinking that it was a secondary carbon.
It is a secondary carbon. I did call it tertiary.
I mean, it still applies to it
The
being
only
chiral, but
prominent one.
I was making sure I
is the
remembered.
Yes, you're right. Because it's only bonded to 2 carbons. All right, just a few more minutes on those 3 molecules then. Identify chiral centers. Correct. There's no hydrogen. sp2 carbon. Never chiral. And when I say sp2 carbon, You could go a mile down the road, and as long as there's one thing different, a mile down the road, they're different groups. But luckily these aren't a mile long, so you won't have to go very far. You really won't. Biggest thing. So you're right on this one. I'll give you the choice if you want it.
Oh, we're talking about like the entire.
Okay, I think most of you have had enough time to go through this. Alyssa, did you find the chiral carbon? Yes. Are you talking about this center? No. All right, so let's start with this polymer precursor. This compound, how many did you guys find? 2? And they were the same chiral center reflected in this molecule, correct? Here's one. Here's one. So CH3, never chiral. sp2 carbons, never chiral. sp2 carbon, never chiral. What's this? CH2, never chiral. What's this? CH2, never chiral. sp2 carbons, never chiral. What's this? It's got 2 methyl groups, not chiral. It's basically a CH2, but it's a CH3 2. So then we get to this guy. This has CH2O, CH2O, OH, H. Boy, by the way I described it, those aren't different. CH2O on either side is the same group. Yeah? Well, then I can just look further. That's not CH2O, that's CH2 ester. And this is not CH2O, that's CH2 ether. Different groups. Ester, ether. The distinction actually lies at the carbonyl and the ether carbon. Different groups. Hydrogen, oxygen, ester, ether.
It just kept going until like you're allowed to go as far as you want. Identify a point of difference.
Correct.
Okay.
Like here, we're not identifying a point of difference until these carbons.
So if it's just like a super long alkane, but like the one on the end is like one, and the one on the end is the other, they're like, they would still be.
I told that group down there, you can go a mile down the road, and as long as you find a difference there, they're different. You will never have to. This is about the longest you'd ever have to go. All right, what about in this? I really don't think I'm doing its name justice. Tretinoin? Tretinoin? Trenton Noen. Thank you. Any chiral carbons? No. There's a whole lot of sp2 carbons going on in this chain, so we can ignore them. I'm really interested most in this group right here, but that's basically the same as this group right here. That's not chiral. In fact, I said that this one was not chiral because it had 2 methyl groups. That's just the easy way out. This has 2 methyl groups, easy, not chiral, achiral. But this one's different, right? It doesn't have 3 distinct groups. Like this has 3 distinct groups. This part of the ring, 2 methyl. This carbon only has 2 distinct groups. Methyl and this huge whatever the heck that is, right? That's reflected on both sides of this carbon, which makes that carbon totally achiral, definitely achiral. All right, then what about an ibuprofen? Well, let's see, how do you say that? Ibuprofen. Ibuprofen. Do you guys see in this name some parts of its nomenclature? What is ibu trying to tell you? Isobutyl. Here's the isobutyl group right here. What about profene? Does that tell you anything? Honestly, if it was PHEN, that might tell me I've got this phenyl group. And so maybe there was a linguistics error there where it's supposed to say ibuprofen for phenyl, but it doesn't. It says F. Regardless, the rest of the name does not do much to help us understand the rest of the structure. But the ibu part actually does tell you that there's an isobutyl, whether you would have picked up on that or not, because it's not very clear. How many chiral carbons? Right there. Here's an achiral carbon because it's got 2 methyl groups. Achiral because it's CH2. Achiral because it's sp2 all the way around the ring as well. 1 chiral carbon. Great. All right, so we can identify chiral centers in bond line structures. Now I want to work together with you because we're not going to do this very often, but I want to work together with you to look at chiral centers in sugars. Do you remember the name of this projection? Fisher projection, or I would have called it fishbone projection. Can we identify chiral centers on this? Is it easier or harder? Easier? Because they're all laid out explicitly. Pick a carbon, any carbon. How about this one at the top, C? Is it bonded to 4 different groups? It's sp2. Remember that this is an abbreviation for an aldehyde. So, not chiral. Can't be chiral, it's sp2. Let's look at this carbon. Is it bonded to 4 different groups? Aldehyde, hydrogen, alcohol, the rest of the sugar. Chiral. How about this next one? I've got a CHOH, a CHOH. Those are the same group. So let's not stop there. This is followed by aldehyde. This is followed by another CHOH. Those are different groups. I mean, to be fair, is this the same as this? No. This has only got 1 alcohol. This has got 3. Definitely different groups. This carbon is chiral. How about the next one? 4 different groups?
You just have to flip what you just did, the circles.
Exactly. And the last one, 4 different groups? And how about this C at the bottom? 4 different groups? No. So this, not chiral, and this, not chiral, but these 4 carbons in the Fisher projection are chiral. It actually is easier to tell when something is chiral or achiral in a Fisher projection because all of the atoms are laid out and you don't have to assume any hydrogens. You don't have to run into this issue of accidentally adding hydrogens either. There is actually a test. I don't go through this in my OChem 2 class, but the professor I TA'd for in grad school, she always talked about this in OChem 2. There's a test you can do with sugars where you can actually change both ends here to be carboxylic acids. And what that does, it leaves some of these carbons as chiral, but if there is a center carbon that now has the same number of groups above and below it, it takes the carbon from being achiral, it takes the carbon from being chiral, and it actually makes it symmetric on either side, and it makes it achiral. Changes its properties, allows you to analyze the sugar in a different way. This is not the same sugar. All of those chiral centers are flipped, correct? Because there is assumed perspective here. All of these H and OH groups are pointing out towards you. And so the only thing that changes from here to here is that all of those groups have swapped sides. That's just like the example we saw at the end of last class. And so I do want you guys to take this down as a note in terms of chiral carbons. Swapping any two groups flips the absolute configuration. Just like how in that molecule we finished at the end of last class, the Cl and the H have flipped places, and the configuration is different. One is R, one is S. Here, every single chiral carbon has swapped only H and OH, which means all of those absolute configurations are different from one structure to the next. Those are not the same molecule. They have a different relationship. What is the relationship between this middle sugar and this sugar on the right? Are they the same? Do all of their chiral centers flip?
No, it doesn't look like the absolute configuration.
Only one of them flips. All of the other ones stay the same. They have a different relationship. In sugars, it's called epimers. We won't have to talk about it much. But I want you to see how these actually help, they give you some perspective. Now here is sugar in a cyclic form. Instead of linear sugar, we're looking at cyclic sugar. Can you tell me how many chiral carbons? To clarify, earlier we had 1, 2, 3, 4. How many chiral carbons in this cyclic sugar? Is there any symmetry in this ring? Is there any place where I can say, this side of the ring reflects into that side of the ring? This oxygen that's in the ring really throws things off. I'd have to put a plane of symmetry that goes through it because I can't reflect the oxygen into anything else. But if I put my plane of symmetry through it, I've got this CH2OH that does not reflect on the other side. Notice just next to the oxygen, that's an alcohol, primary carbon. That's a CH2OH, secondary carbon. There's no symmetry in this molecule, which means any carbon you think is probably chiral is probably chiral. This one, chiral or achiral? chiral. Here, chiral. Here, chiral. 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 That's CH2. Good catch. CH2, achiral. And now you can go through and prove it that these 5 carbons are chiral because they are bonded to different groups. There's no one side of the ring that is the same group as the other side of the ring. Look at this carbon here. It's bonded to a CHOH and a CHOH. But those are not the same because this is bonded to CHOH ether, and this is bonded to CH2OH ether. From this carbon's perspective, the first point of difference is actually here. All right. What I want to do now is actually have you turn back to oxycodone and work on analyzing the absolute configuration of the 4 chiral carbons in oxycodone. We said earlier that oxycodone has 4 chiral centers. You know what? We're going to go through it together. Because there are tips I didn't teach you yet to it. Do you remember the rules for establishing the absolute configuration? The Kahn-Ingold Prelog rules. Good. Rank the groups by highest atomic mass. At the first point of difference. Rule number 2. Good. Place priority number 4 in back. Then determine rotation from 1 to 2 to 3. Do not try to get 4 into rotation. All right, so because there's not a lot of space on your sheet next to oxycodone, I might encourage you to do something like this. I'm going to label this carbon as carbon 1, and I'm just going to copy down what I need to about carbon 1 so that I can see what I'm looking at, rank my groups, but not have to do much more than that. So here's the selection of carbon 1 that I'm going to copy down. If you want to try and do it next to the structure, you can, but if you need a little bit more space, you can do that too. What is my highest priority group? Nitrogen has priority over carbon, carbon, and hydrogen. So here's priority number 1. What is priority group number 2? The what? Good. I'm stuck between carbon and carbon. Since that's not a point of difference, I need to look for the next highest atomic mass. From this carbon, the next highest atomic mass is oxygen. And from this carbon, the next highest atomic mass is carbon. So my highest atomic mass here wins out at oxygen. This is group 2. This is group 3. Shoot, do I not have a group 4? It's the assumed hydrogen. And where is that assumed hydrogen? I know it's placed away from me because I have a group coming towards me and 2 groups in plane. There's only one place left, and that's away. I'm not even going to draw it in because I don't need it. It's where I need it to be. 1 to 2 to 3. Carbon 1 has what configuration? R. That's the top half of an R. That's how I like to remember it anyways. Okay, I gave you this tip towards the end of yesterday, which is tip 1. If your lowest priority is coming towards you, follow all of the rules, but assign the configuration opposite of what you see. Here's what I want to say, because I left off with this, and it didn't inspire you like I wanted it to. If you were the numbers sitting on the face of a clock, what direction are the hands of the clock moving? Clockwise. When you look at the clock, which way do the hands move? Clockwise, hopefully. Now I want you to sit yourself behind the hands. Which way do they move? Counterclockwise, by the perspective of the hands. So here's what I'm going to do for you guys. I'm going to move my hand clockwise. And now I want you to look at me from behind. Which way is it moving? I told you it was clockwise, so which way is it moving? But I told you it was clockwise, so which way is it moving? Perspective is everything. If your priority group is not facing back, you're going to get the wrong configuration. So here's actually an advantage. If you know your priority, your lowest priority is coming towards you, it's just backwards. Assign 1 to 2 to 3 and assign it opposite. Yeah? So what's the highest priority for this chiral center 2? Anybody? Highest priority group? The hydrogen is the lowest priority group. Oh, I mean flip the rotation. If it looks like it's rotating clockwise, you're actually looking at it backwards. It's rotating counterclockwise. So don't flip the rankings. What I mean is follow the rules, 1 to 2 to 3, but just assign it opposite of what you've determined. So what's the highest priority group? There's no OH. I've abbreviated it. It's an ether. The oxygen. But remember, you never have to describe more than one atom. The oxygen is the highest priority group. And we already said the hydrogen is the low priority group. What is higher, a quaternary carbon or a carbonyl carbon? Wrong. They're both carbons. Yeah? So you look for the next highest priority group. What comes after a quaternary carbon is always a carbon. What could I go for after this carbonyl carbon? Oxygen. So what's higher? Carbon or oxygen? Oxygen. Priority 2, priority 3. I'm going to ignore priority 4. I never determine that in my rotation. 1 to 2 to 3 is what? It looks S. It's like looking at the clock being a number. It looks S, so we assign opposite. That is an R absolute configuration. You agree? You guys disagree? Are we following rule 2 correctly? No, we are not following rule 2. So we're looking at this, seeing it go like this. But we agreed. You're looking at it wrong. You're looking at it backwards. Which way is it actually rotating? R. Correct? Do you know which way hurricanes spin in the different hemispheres? They spin different directions. Like in the northern hemisphere, hurricanes spin clockwise. But I've always wondered, is that just from space or is that from the ground too? Because a hurricane spins a different direction if you're looking at it from the top versus the bottom.
Yeah.
The same with a tornado. When you're looking at the ground, a tornado is spinning a different direction than if you look at it from the top. Like a clock. If you look at it from here versus from behind it, it's spinning a different direction. That's what rule 2 is doing. Your perspective is just wrong. So follow all the same rules, but just flip it. All right, now I want to look at, we can really look at either of these next two, but I'm going to look at this one first, because it's going to help me actually get 2 of my tips out of the way. Tip 2, if the lowest priority is in plane. Notice I'm just using some abbreviated terminology here. Dashed lowest priority, wedged lowest priority, and this is in plane lowest priority. You cannot determine R or S. It's impossible. Well, okay, so you either have to rotate it into a different conformation where the lowest priority is pointing away from you or pointing towards you, or you can do this thing. You can swap the positions of 4 with whatever is in back. So I'm just going to say swap the positions of priority group 4 with the group that is pointed away. If you don't have a group pointed away, you can just swap it with anything, really. This is actually going to be harder for oxycodone than I want it to be. If you swap 2 groups, what happens to your configuration? It flips. So if I put priority 4 in back artificially, if I imagine to break the bonds and swap them artificially, then I'm not actually assigning the true configuration. Yeah? I'd be setting it up for priority 4 to be in the back, but I just swapped 2 of the groups. So if I assign R, it's actually S, the actual version that I'm looking for. If I determine that it's S, then the version I was looking for before breaking the bonds was actually R. So swap the position with what's in back, assign opposite again. Okay, but here's a funny trick, but funny weird, not funny haha. If you swap position 4 with whatever is coming forward, then you can break 2 rules at once and get the right answer.
But you can do double negative.
It's double negative in chemistry, in conceptual chemistry. Because remember, you're swapping 2 groups, you are changing the configuration from what you want to determine. So then put priority 4 in front and assign it wrong anyways, because then you're actually assigning it correctly. Yeah? All right, we're going to apply that tip with our carbon number 3. But here's my last tip for these. Quaternary carbon is the highest priority over tertiary carbon, over secondary carbon, over primary carbon. That only works if you don't have heteroatoms. As long as you're looking at just alkane things, all you have are hydrocarbons, a higher substituted carbon will always have higher priority. Why? Because this primary carbon, the next highest mass atom is always going to be a hydrogen. But a quaternary carbon will always have a higher number of carbons than any of the other groups. Quaternary will always have one more carbon to beat out the other lower substituents. So if all you're doing is comparing hydrocarbon chains, higher degree of substitution, higher priority. Let's apply that here in chiral carbon 3. Now this one I actually am going to keep in here. Can I assign priority number 1? Oxygen. Oxygen beats out carbon, carbon, and carbon. How can I rule out those carbons? Well, I can look for the next highest mass. This is only bonded to carbons. This is bonded to 1 carbon and 2 hydrogens. So we can say that this is quaternary, this is secondary, but this one is bonded to a nitrogen. Nitrogen wins out. Here's priority number 2. Now I'm down to comparing my last 2 groups. A quaternary alkane carbon, that's not the one I'm pointing at. A secondary alkane carbon, and a quaternary alkane carbon. No heteroatoms attached. Which one wins? Tip 3. Quaternary carbon beats a secondary carbon. Why did the quaternary carbon not beat this secondary carbon? Because there's a heteroatom. Nitrogen wins out. These don't have heteroatoms to fight. So here's priority number 3. Here's priority number 4. Are you surprised that the lowest priority is not a hydrogen group? It's the first one that we're looking at that doesn't have a hydrogen as the lowest priority. It happens sometimes, it's rare. Okay. Notice tip 2, lowest priority is in plane. So I need to do one of 2 things. I need to swap the lowest priority with what's in the back, assign rotation 1 to 2 to 3, but then assign opposite. I actually don't know what's in back. I only have a wedged group. I don't have any dashed groups. So I have to actually follow my weird rule. I'm going to say no more position 4 here, no more position 1 here. Let's imagine that this is where my lowest priority was, and this is where my highest priority was. I am breaking rule number 2, and that's okay in this case, because I also broke some of the bonds. So now I determine rotation, ignoring 4 from 1 to 2 to 3. how does it appear? It appears S, which means the rotation is actually R. But it only appears R because I broke two of the bonds and swapped them. So it's actually yes and no. You usually don't have to go through all these hoops, but you may have to determine configurations. Is it really so complicated? There's several steps, sure, but it's just perspective. It's all perspective.
I got lost when you
Swapped 1 and 4.
Yeah. Well, no. So that makes sense to me how you swapped it. So it appeared as, but then it was actually R. But then why was it not R again?
It wasn't R because I broke the bond from my chiral carbon to my lowest priority, and I broke the bond from my lowest carbon to my highest priority, and I swapped them. I didn't draw it that way. I didn't redraw it, but now we're imagining that this CH2 is actually wedged, and this OH is in plane. So now my rotation is 1 to 2 to 3. Because I broke two of my bonds, I changed the configuration. It was S as drawn on the molecule. I broke those two bonds, it became R. But then I placed the lowest priority in front and analyzed it. So I'm looking at it as if it's S, but with my lowest priority in front, so it's actually R. But I broke two of the bonds to get that, so it's actually S.
This is just kind of a question, so is the reason we're doing it in this way, sorting it by these rules, is it because this is the direction that the heavier part of it is being pulled around?
No, it has nothing to do with its physical or chemical properties in any way. It's just a system of rules to help us all be on the same page. So that when I ask, what are the absolute configurations of oxycodone that need to be there to be metabolized in your body, we can just all follow the same rules to get there. Those are the rules. Kiara.
I just want to clarify, with tip number 2. So because we switched for with a wedge bond, we would assign it as the apparent yes.
Tip 2 is simply, no, I'm sorry, say it again.
So we assigned it, I know you're going back and forth because you're explaining for each of the bonds.
Yes.
But tip 2, since we switched the 4th spot with a wedge,
Correct.
it would be S because that's what was apparent.
That's right.
Okay.
So we didn't need to say, it looks R, so it is R, or sorry, it looks S, so it is R, but it was S originally. We could have just said, because if you know the rules, if you understand the rules, then you could have just said, 2 wrongs make a right, it's S. But I wanted to show you why it was 2 wrongs that made a right. We looked at it backwards, but we also broke 2 of the bonds, 2 wrongs that righted themselves out. Yeah? I hate to say that, but that's the clearest I've ever explained it. It really is. I want to say even in the spring, I had to teach this in 30 seconds. Or 15 minutes. And so that was really challenging. At least you guys get some time to sit on it. Okay, that was a challenging structure, but I want you to look at some of the other molecules on the second page. None of them are quite that hard because the lowest priority group, most of them are not that quite that hard because usually the lowest priority group is in front or in back. Triamcinolone, that does have the lowest priority in plane. So if you wanted to assign that configuration, you'd have to use tip 2, which is a challenge, but it is doable. Listen, I want us to try one more thing. I want us to take this bisphenol A glycidyl dimethyl acrylate, and I want us to draw both chiral carbons with an S absolute configuration. Currently, they do not have an absolute configuration. Why? There's no wedges or dashes shown. Is that what you said? If there's not a single wedge or dash shown, you have no information about how it's oriented in space. This is neither R nor S because there's not enough information. By the way, I think I have some multiple choice questions that are phrased like that. What is the absolute configuration? R, S, neither, not enough information given. Neither and not enough information are not the same. An achiral carbon has neither R nor S. A chiral carbon that doesn't have enough information is either R or S, we just don't have the information for it. I want you to draw both chiral carbons with an S absolute configuration. How would you do it? Start.
Would you connect the extra hydrogen as
As a wedge?
yeah,
Why not a dash?
or a dash? Either way.
How would you know? Let's do this. Let's start by ranking the groups. Yeah? What's the highest group attached to this chiral carbon? The oxygen. Not even the OH by necessity. The oxygen is the highest group. What's the next highest group?
Or the yeah.
Oh, you said to the
Or no.
you said to the ether.
The ether.
So you guys are disagreeing? So we know the difference is not at the carbon. We know the difference is not at the oxygen.
Oh, I agree.
We know that the difference is not at the carbon. Would you agree? So far, all three of those atoms are the same atom. Now what's my next highest atom? Oxygen, then carbon. Yeah? And my lowest priority is the hydrogen that's assumed. So here's where what Maisie said comes into play. I don't know if that hydrogen is wedged or dashed. Let's assume it's dashed. Let's not even show it for now. Let's assume it's dashed. 1 to 2 to 3. R. Ah, shit. So if it's dashed, it's R. If this OH is wedged, in fact, if any of these groups are wedged, it's an R configuration. So what do I want? I want the OH dashed, or in other words, I want the hydrogen there to be wedged, because that means I'm looking 1 to 2 to 3 incorrectly. It looks R, it is S. So do you agree? Dash the OH, wedge the H. Or don't show the H, because then it has to be wedged. What would you do to this side? To make it also S. Nothing? Leave it as is? Not enough information. So you would do the same thing. Dash the OH, wedge the H. Here's what you should do. Assign priorities. Okay, we already did the heavy lifting. Determine the rotation, 1 to 2 to 3. that would be S if we followed rule 2. If the hydrogen is dashed and the OH is wedged. Are you happy with that? On one side, we had this R apparent configuration, so we needed the H to be forward. But on the other side, all of the groups were flipped. Do you know what we did? We essentially took these 2 bonds to the chiral carbon and we flipped them onto this side, which is very similar to swapping the absolute configuration. But this time we wanted to keep the same configuration. So if these groups are going to flip sides, these groups also have to flip sides. Correct? If I break 2 bonds, if I swap 2 bonds, I change the configuration. If I swap all 4 bonds, configuration stays the same. So, dashed OH on the left, wedged OH on the right, both are S chiral centers. Very fun. All right, why don't you guys take a quick 5-minute break, even if you're not going to leave. Get up, get your blood flowing a little bit. We got some fun terminology coming up next. That arrow looks R, but it's breaking rule 2.
How do you know that on the left side the line is dashed? That's what I'm not understanding.
I wanted to show it S.
So if you did it the other way, or if you made that one,
If this was wedged,
yeah.
then it would have been R.
So that would have made it so that one would have been R and that one would have been S, or would they both be R?
If this was wedged, OH, and if this was wedged, OH, then this would be R, and this would still be S.
Yeah, but like if you did the opposite switch, where like if you made the left one
Wedge,
and the right one
dash,
that
R,
would be,
R.
I get it now. Okay, got it. So this was just an explanation. So like with the different.
This was an exercise in taking a carbon that doesn't have a chiral center and showing it with an absolute configuration. I almost never get enough time to teach how to do that.
Yeah, that makes sense.
I'm so happy.
Yeah.
No, don't look at that.
Position 4 would be hydrogen originally, or swapping that?
Yes.
Okay.
Yes and no. What do you
So,
I'm just swapping the H and the Cl. It's not so much about highest or lowest priority. I'm just swapping 2 bonds and the configuration. You're talking. I'm sorry. Are you talking about this?
no.
Oh.
That. Yeah.
I thought you were talking about this.
No. That.
Say it again.
Position 4 would be the hydrogen,
That's true.
and when you swap it,
I'm not swapping it. Or are you saying like over here it kind of swaps because now it's back?
wait,
Yeah, me too.
so,
That was a crazy shoulder.
I'm not. I drew in that hydrogen. I'm not swapping it with anything.
so it's originally going this way.
It looks like it's R.
It looks like it's R.
I'm breaking rule number 2.
Uh-huh.
So it's actually S, as I've drawn it. It wasn't R or S before.
The OH.
Yes, I pushed the OH back. I have the hydrogen coming forward. That's 1, 2, 3 in a clockwise position. Breaking rule number 2. I have to look at it from this side. It's actually counterclockwise. Here, I'm looking at it correctly. 1, 2, 3, hydrogen going back, that's S.
Okay. So you're saying that one's technically S if you're looking at it from the other direction.
It is S in the same way that a hurricane rotates clockwise from the sky and counterclockwise from the ground. They're rotating the same direction.
But if you're looking at it straight on like this,
It's
this side would be R and this side would be S.
it's S in the same way that this is my right hand if my palm is coming forward. It's all about the perspective we've agreed on, the rules we've agreed on. And you agreed on it when you paid for this class.
Okay, I guess my question would be,
Because you were asking about swapping the groups. And I think I made some confusion when I said swapping the groups earlier. So maybe I can try to show it better like this. So you see how on the left chiral carbon I have the ester and the ether groups. And on the right chiral carbon, it's the ester and the ether groups. Those flip sides. But I don't want it to have a different absolute configuration. I want it to have the same configuration.
which is why you made the H and OH different on this side to show the perspective.
If I had OH and H, like I do there,
Yeah.
this would be S and this would be R. So I can put this to be OH and this H, which means I've swapped these two groups, but I've also swapped these two groups. I've kept the configuration the same.
I guess my confusion is like, how would you know to push the OH back on that side?
We didn't. I mean, like, we wanted to aim for it to be S.
Yeah.
I can't change the position of 1, 2, and 3. They're always going to be oriented like this. I want it to be S. How can I get it to be S if they're always oriented clockwise to each other? I have to break rule number 2. I have to look at it wrong.
So bringing the hydrogen forward would do that?
Yeah, because rule number 2 is always place the hydrogen back. Sorry, always place the lowest priority back.
Oh, because that was technically number 4.
It is.
Place it forward so that.
Oh my god.
Take 1.
It's my favorite time of the day.
I'm not breaking any bonds.
6:16.
Okay, because that's swapping, you just decided to assign.
Correct.
Okay, that's, sorry.
Favorite time of the day, 6:16.
All right, guys. Are you ready? So I just want to make sure. I want to make sure I've made this as clear as I can. This is not R or S. There's not enough information to know. We were on an exercise to show it as S. And this side was actually very easy. I cannot change the position of 1, 2, and 3. They're always locked in this orientation. But I can control the position of the wedge and the dash. So if you ever need to draw a chiral center, I mean, you can do a bit of guess and check. Draw it this way, see if it obeys your rules. And if it's wrong, just swap 2 of those groups and you will change its absolute configuration. This one was easy because it already looks S, so I just need to make it obey that rule. Put the lowest priority in the back. This one was hard because it already looks R. How can I get a carbon that already looks R to actually be S? I need to look at it wrong. I need to look at it breaking rule number 2. I'm applying tip 1 backwards. I'm taking that lowest priority group and I'm setting it forward so that even though it appears to be R, it's actually S following the rules. Yeah? If I could take this whole molecule out And if I could spin it around for you, this hydrogen that's coming forward would end up pointing back. This molecule spins around just like that. So if you assigned this S and you want this to be S, spin it around. That hydrogen's coming towards you. Yeah? All right, we're going to get into some really fun relational things with molecules. First, molecular descriptors. These are terms that are applied to one molecule. You look at a structure and you can apply these terms. Chiral. Yes, carbons can be chiral. Those are carbons that are bonded to 4 distinct groups. Molecules at large can also be chiral, which means the definition of chiral is not being bonded to 4 distinct groups, because how can a molecule be bonded to 4 distinct groups? The definition of chiral, actually, do you guys remember, or a synonym for chiral? Good point. It is handedness. It's literal translation. But another synonym? Asymmetric. That's what chiral means. A molecule that lacks symmetry. Lacks a plane of symmetry. All right, I'm not going to lie. It can be pretty challenging to look at a structure and know if it lacks a plane of symmetry. So here's an easier way to identify a chiral molecule. It has at least, so I'm going to say greater than or equal to 1 chiral center. Both of these things must be true. It must have at least 1 chiral center. It must lack a plane of symmetry. Our next term, achiral. This has at least 1 plane of symmetry. And lacks any chiral carbons. Pretty easy, right? Just exact opposites of each other. So let's make it more challenging. These compounds are often called achiral meso. Although the achiral can be dropped and they're sometimes just called meso. I don't know meso, I don't know its word, it's etymology. So if meso rings a bell to any of you, let me know what it means. A meso compound has at least 1 plane of symmetry and it has at least 2 chiral carbons. A big help here in identifying meso compounds is that those chiral carbons will be symmetric to each other. Here's a Venn diagram showing this family relationship. Not all achiral compounds are meso, but all meso compounds are achiral. Meso compounds are not chiral. Because why? Chiral compounds lack symmetry. Meso compounds have symmetry. Chiral compounds have at least one chiral center, true. But meso compounds, their chiral centers are reflected into each other. So despite having chiral centers, they are achiral compounds. So let's take a look back at our sheet. Loss zone. Chiral, achiral, or meso? How does it obey the rules of achiral? No, but good try. Try the other one. It lacks chiral carbons. Loss zone has exactly 0 chiral carbons, correct? Stop. It has none. So the plane is actually very hard to see. The plane is in the plane of these rings. This ring is entirely planar. This ring is mostly planar. And so there is a point where this hydrogen wedges up and this hydrogen wedges down, and those get bisected. But the rest of it is the plane of the molecule. That's the plane of symmetry. The top half of this molecule is symmetric to the bottom half of the molecule, right? In the same way that the top half of a hula hoop is symmetric to the bottom half of a hula hoop. Yes, hula hoops, you can have an infinite number of other planes of symmetry, but you could also cut a hula hoop right in half. And the little bit on top is symmetric to the little bit on bottom. Oxycodone. Chiral, achiral, or meso? Are you looking for a plane of symmetry right now? Because it should be pretty obvious to see that there can't be one. The best shot would be right down the middle, but an aromatic ring and a cyclohexane ring, those do not reflect. So what would you say? Does it have at least one chiral center? Yeah, definitely. Chiral. Bisphenol A. Ooh.
You can split the molecule directly down.
Trick question. Not enough information given. In this form, there is not enough information given. Let's imagine a world where the two chiral carbons are both wedged alcohols. Yes, there is a plane of symmetry right down the middle where this chiral center reflects into this chiral center. Funny thing about those chiral centers, this is R and this is S, which means this rotates like this rotates like this. The rotations are symmetric. The chiral centers are symmetric, the rotations are symmetric. But what about the world we were just living in, where this OH was dashed? Is there a plane of symmetry now? That's like looking at one OH coming towards you and one OH going back. Can't reflect them into each other. They don't overlap. That's your hands doing the turtle, right? Bisphenol A has both a meso stereoisomer. There are combinations of absolute configurations that make it meso, and it has a chiral stereoisomer, two chiral stereoisomers. So if this was given to you, chiral. If this was given to you, meso. And if this is given to you, not enough information.
So would you want to put not enough info, or would you give all the options?
So first of all, I would never put a question like this on an exam that's not a multiple choice. So you would have chiral, achiral, meso, not enough information as your options. And if you could take a compound and show it both as meso and as chiral, then that means there's not enough information. Yeah? Tretinoin. Chiral, achiral, or meso? Achiral. Why? 0 chiral carbons. You want to try and find that plane of symmetry again? It's going to be very similar to what we just saw, where most of this is all in the same plane, because they're all planar atoms. Here's an interesting thing about that plane of symmetry rule. It only needs to have a plane of symmetry in at least one conformation, which means that chairs that are typically this conformation or that can have a boat conformation where they have a plane of symmetry, and that makes them achiral, even if it's not their most common form. Ibuprofen. Chiral, just one chiral center. How about this sugar on the left? Chiral, achiral, or meso? Which one is it not? It's not achiral. But we also said it doesn't have a plane of symmetry because this aldehyde and this alcohol do not reflect into each other. But again, this is another useful component of the Fisher projection, is that you can more easily look for symmetry in the top and bottom halves. But the aldehyde and the alcohol, no symmetry, chiral. What about when I flip it to its mirror image? Still chiral. What about when I flip just one of those chiral centers? Made it even less. It makes it more obvious that it's not symmetric. What about in that cyclic form?
We already discussed how the oxygen makes it.
No symmetry through that ring. Chiral. Because again, you've got that on one side of the oxygen, you've got this OH, and you've got this CHOH. So fun. Okay, that's descriptors. We look at these compounds and we call them chiral, achiral, or meso. Now we have molecular relationships. How many compounds do you need to have a relationship? At least 2, yes. We've actually already talked about molecular relationships to an extent. We said that compounds that share the same chemical formula but have different connections are structural isomers. That's a relationship. Same chemical formula, different connectivity. We didn't talk much about this, but molecules that are the same exact structure, simply rotated around each other, those are called conformational isomers. They're the same molecule. They're identical molecules. They're just in a different conformation. Pretty easy. And then we get into this big class of structures called stereoisomers. That's where we are right now. The first stereoisomer I want to talk to you about is the enantiomer. Once again, I actually don't know the etymology of this word, so I'm not sure why they picked this. Because this is another place where handedness would have come in handy. No pun intended. Your hands are enantiomers of each other. Your hands are non-superimposable I always forget how to spell this. Posable. Thank you. Mirror images. They have to be mirror images. If they are not mirror images, then they are not enantiomers. They also cannot be superimposed. If they are mirror images, and they can be superimposed by rotation, translation, anything, any sort of movement without breaking a bond that can get them to be superimposed, then they are enantiomers. Here's a nice tip for finding enantiomers. All chiral centers flip. One enantiomer has RS. I'm sorry, I'm going to pick a different one. One enantiomer has RR. The other enantiomer has SS. One enantiomer has only S. The other one has only R. These two chloro compounds that I've been showing you, there's only one enantiomer. Sorry. There's only one stereoisomer. There's only one chiral center. When it flips, the enantiomer is formed. The enantiomer for oxycodone, all four of those chiral centers flip. The enantiomer for ibuprofen, that one chiral center flips. The enantiomer for these sugars, all chiral centers flip. These two sugars are enantiomers of each other. The next relationship that we have is diastereomers. These are non-superimposable non-mirror images. Non-superimposable, non-mirror images. It's like your hand and your foot. Same number of digits, same number of bones. I might be wrong on that. No need to correct me. But they're definitely not superimposable, and they're definitely not mirror images. They're constructed in drastically different ways. Here's a good way to look for this. At least one chiral center is consistent. At least one chiral center is flipped. In oxycodone, if all I changed was the stereochemistry of this hydrogen so that it was dashed, I've created a diastereomer. If all other chiral centers stay the same and just the hydrogen changes, diastereomer. Look at the sugars. These two are enantiomers. What is the relationship between these two? Diastereomers. Notice how 3 of the chiral centers flip and 1 of them stays the same. They're not superimposable, but they're also not mirror images. These are diastereomers. And what about these 2 sugars? What is their relationship? You can say it with me. Dia. Say it with me. Dia stereomers. I know a lot of people pronounce it diastereomers. But that one actually, diastereomers, it reminds me of these 2 things. Dia, 2 things. 1 chiral center is constant, 1 chiral center is flipped. In this orange set, 3 of the chiral centers are constant, 1 of the chiral centers is flipped. Diastereomers. You cannot use the term diastereomer or enantiomer unless you are looking at 2 compounds. It's like looking at Nicole and saying, you look like a twin. Right? Doesn't make any sense. But Nicole and her twin, oh, you 2 look like twins. That's a relationship. You can look at me and call me chiral. That's a description. But you can't look at me and call me a diastereomer. Yeah? All right. There is this equation. I swear there's not a lot of math in this class. But you can actually calculate the number of stereoisomers that a compound can have by taking 2 to the power of n where n is the number of chiral carbons that you have. No, it's never that easy. You have to subtract 1 stereoisomer for any form that is meso. Meso compounds do not have enantiomers. That's a good idea. 2 to the power of n minus 1 m. M is the number of meso forms. And if there are 0 meso forms, 1 times 0 is 0. You could. Why is it that a meso compound cannot have an enantiomer? A meso compound already has a plane of symmetry. It already reflects inside of itself. So if you reflect the molecule at large, then it's just going to be the same thing. Let's take a look at that bisphenol A again. Here is a meso form, correct? What would happen to those chiral carbons if I took this molecule out and I flipped it over backwards? How would the stereochemistry change? They'd be pointing away, yeah? And what if I put a mirror plane behind this molecule? How would it look inside the mirror? I'm just going to abbreviate a little bit here. In a mirror, things that are far from you behind you are far from you through the mirror. But things that are on your left are still on your left. Things that are on your right are still on your right. That's if you're looking at a mirror. Or if you're standing next to a mirror, things that are on your left are actually on the right of the mirror. Things that are in front of you are still in front of you in the mirror. Mirrors flip front and back or left and right. So this mirror is flipping these OHs. These OHs are coming towards me, so in the mirror, it's actually going to look like they're going away from me. The OHs are going away from the mirror both times, coming towards me here, away from me here. But they're the same thing, because as Aiden said, if I flip this over, those OH groups point back. Let's make another mirror plane. Let's just put the mirror plane here. Again, I'm just going to abbreviate a little bit of this. All I've done is flipped left and right. But my OH is still coming towards me. I'm going to be able to slide this whole thing over and superimpose it. Meso compounds are superimposable with their mirror images. And I want to give you guys kind of a class of meso compounds that are surprisingly meso. This compound is meso. I don't see the plane of symmetry yet. But if I rotate into a new conformation, if I go from zig-zag to zig-zig, this carbon's not rotating, so its stereochemistry stays the same. This carbon is rotating, so its stereochemistry rotates with it. It doesn't appear to have a plane of symmetry in this conformation, but it is a meso compound. Remember, only needs to have a plane of symmetry in one conformation. So here's what I was going to have you do with the back side of this sheet. I know we're running low on time. I guess I was kind of debating on having you identify chiral, achiral, and meso, potentially assign all absolute configurations, but I was also going to encourage you to draw the enantiomer of the compounds that you see, or draw a diastereomer of the compounds that you see, and practice taking some real-life compounds and drawing them out. And I'm also really sad, so I'm going to make you guys do this as you leave. Sorry, because I spent a lot of time on this. I have these molecules in pairs or threes. I want you to, I want you guys to come up and grab a compound and then find the corresponding compound in the room. You're going to match by colors. And I want you to decide if you are looking at enantiomers of your compounds, diastereomers of your compounds, or the same compound. So this is your exit ticket. Once you have found your corresponding compound, you can tell me whether you have an enantiomer, a diastereomer, or if they are the same exact compound. And then you are free to go. I'm hearing it.
Here, I'll pretend to be.
Wait, did I don't know what I did with it.
Oh, it's over there.
Oh, they're just being slow. Also, I did lie. There was another class that I wanted you to look at. That's just cis-trans, which by far is the easiest type of stereo relationship. But I've put a specific type up here. This is an achiral molecule. There's a plane of symmetry that runs 1 to 4. And so these are not enantiomers. They're technically not diastereomers either, although some might classify them as that. They are not the same compound, though. They are cis-trans isomers. That's the last type. It's very simple. And you can apply cis-trans to any di-substituted ring. But many di-substituted rings are also chiral. You never apply cis-trans to linear conformations because this looks trans, wedged and dashed, but just rotating it makes it look cis. Chairs will never rotate like that. Okay, did you find your pairs? What do you guys have? Enantiomers, diastereomers, or identical? Can you see how you can't get them to superimpose no matter what? Mirror images. What do you guys have? Yeah, might be easier to put them in a zigzag conformation, so the carbon chains are really easily lined up. Enantiomers? No. No. Those are superimposable. Those are identical. So guys, pay attention to this one. Identical. They are mirror images, but these compounds are identical. Why? That compound is meso. It's got a plane of symmetry. Meso compounds cannot have enantiomers. They can have diastereomers, but they cannot have enantiomers. Good work. What do you guys have? You have diastereomers. You have a meso form and a chiral form. And where'd my other green one go?
Right here.
Oh. So what do you guys have relative to this? What's their relationship? Yours is meso, mine is not. But meso is not a relationship. You do not have enantiomers. Your meso form has no enantiomer. They're not related. They have the same chemical formula, same connection of the atoms. This is 2,3-dichlorobutane. Are they mirror images? What do we call non-superimposable, non-mirror images? Diastereomers. You have diastereomers. Congratulations. Good luck on your unit test this weekend. What time does your unit test open? Tomorrow morning. Good luck. Have fun. I'll see you all Monday.
Thank you.
Have a good weekend. I worked way too hard on that, and I wanted you guys to have more time with it. Oh, middle. So
meso.
a plane of symmetry in the middle.
So it's the middle between both. But it's connecting both at the same time.
I don't know if it's the middle between both, where it's both chiral and achiral.
Right.
I wonder if maybe it's saying it has a plane of symmetry down the middle,
That might be more.
and so it's a meso compound.
Yeah.
Interesting.
So that's what it's Greek.
Oh, thank you, Peter. All right, did I get your guns'?
Yeah.
Great. I'm gonna put this on YouTube. Enantiomer, diastereomer. Trying to say it loud enough so it catches it over there. I'm not even doing a good job of holding it. No, that's okay. Thank you though.
I can monitor it for you.
Identical.
Yeah, it's in frame. It's in frame.
Sweet. All right. I think that's it.